All right, thanks very much, Lee. So I'm enjoying this workshop very much so far. It's some very excellent talks, really interesting stuff. Today I'll be talking about effective interactions between nuclear clusters. I actually added a couple of slides at the end because of the discussion we've been having so far. So I'll try to cover all my material a little bit early. So I'll talk about lattice effective field theory, how we do the calculations. Then I'll speak a little bit about what I mean by local versus non-local interactions. This will actually end up being important for nuclear binding. Then I'll talk to you about how nuclear physics is close to a quantum phase transition. Then I'll talk about the effective interaction between nuclear clusters and nuclear clustering in the spectrum of carbon-12. I will summarize, but then I added a couple of slides on cluster entanglement, as well as model independent measures of the alpha cluster geometry. So this is how we do the calculations. We put protons and neutrons on a lattice between, let's say, half a Fermi to 2 Fermi in lattice spacing. And we use chiroeffective field theory to do the, on a supercomputer to do the calculations. If you want to learn more about the details, you can either read this now rather old review that I've written, or this textbook that my collaborators Timo Lede and Wolf Meissner have written. So we put chiroeffective field theory on the lattice. That's essentially the idea is we're interested in the low energy physics of the nucleons interacting with each other. And so at leading order, we have then the long range exchange of pions, the 1 pion exchange, as well as S-wave contact interactions like this. And then at higher orders, we have things like 2 pion exchanges and things like that. But the way we do the calculations on a supercomputer is by Euclidean time projection. Essentially what we do is take the exponential of minus ht, or tau. As tau gets large, we see the low energy states of our theory, and that's how we do the calculations. Okay, so let me now briefly mention what I mean by a local interaction versus a non-local interaction. So a local interaction is something like the Coulomb interaction. Now, generally speaking, we can have a two-body interaction where R is the incoming separation vector between the 2 particles, and R prime is the outgoing separation vector between the 2 particles. If R prime is equal to R, then we have not moved the particles at all. This is like the Coulomb interaction, and this is what I call a local interaction. A non-local interaction is one where the center of mass of the particles remains constant, remains fixed, but the positions, the relative positions of the particles can move. So this is a non-local interaction. You can think of this as simply not being diagonal in position space, or you can actually think of this as a velocity-dependent interaction. Okay. Now let me tell you a tale of two interactions. So I'm going to talk to you about interaction A and interaction B. Both are at leading order in chiroeffective field theory, so they're quite simple. They both have the same 1 pion exchange potential and the same Coulomb potential, but the difference between interaction A and interaction B resides with their short-range interactions. So interaction A will have only a non-local short-range interaction, so something like this here, where interaction B will have a local plus a non-local plus a local interaction. If you want to read more about this, you can look at this PRL from 2016. So let me first show you that they both sort of describe the system up to 4 nucleons quite in essentially the same way. They agree more or less on the triton binding energies, the helium-3 and the alpha particle. Okay, so they underbind the triton and the helium-3 because of lattice artifacts. That's what we understand this quite well. That's not really the point of this exercise, but they reproduce the alpha particles relatively well. But when we go to more than A equals 4, we go up to, let's say, beryllium 8, carbon 12, oxygen 16, neon 20. B, with Coulomb included, does a pretty good job of describing the experimental binding energies of these heavier nuclei, these alpha-like nuclei, alpha conjugate nuclei. But interaction A seems to have quite a lot of difficulty. It's the binding energies are quite a bit off. They're severely underbound. So we wanted to understand why this was happening. Why is it that at the level of the 3 and 4 body system, everything looks fine, and then A somehow just does a terrible job now?
Right.
So in order to look at that, yeah. Okay. So in order to look at what's going on here, we actually turned off the Coulomb interaction, and we just look at the leading order interactions of the leading order binding energies, and took ratios of these leading order energies to the binding energy of an alpha particle. And what we find are these integer ratios, 2, 3, 4, 5. And so what we concluded was that with this interaction A, we somehow accidentally made a Bose-Einstein condensate of alpha particles in our periodic volume. Okay, so to try to confirm that this was actually the case, we then did a calculation using a technique called the adiabatic projection method. We calculated alpha scattering in the S wave, and we did confirm that in fact, for the S-wave scattering for interaction B with Coulomb, we do a good job of reproducing the empirical phase shifts here. Okay, you can see the comparison with Absal, and it's doing quite nicely. But when we take interaction when we take interaction A, we essentially have, we actually have a repulsive interaction at higher energies. And in generally speaking, we have a very weak interaction at low energies and a little bit of repulsion at higher energies. So this is consistent with the idea that the interactions of the alpha-alpha interaction is too weak, and we've produced an alpha gas. So what we have shown is that there's actually this quantum phase transition as I change from a local interaction to a non-local interaction. This side over here is a local interaction, and this side over here is a non-local interaction. We can actually go through a quantum phase transition where we have the alpha gas here. And at this point, the scattering length for alpha-alpha is 0. At this point here, alpha-alpha scattering length is infinity, or what's called the unitary limit. And that's when we get these nuclear liquid droplets to form. Okay, so we wanted to understand a little bit better what was going on with these effective interactions between the bound states. So we did this little calculation for a simple 1D system of dimers. And what we did was we used what we call numerical tweezers by actually pinning down the spin down, so we have spin up and spin down and spin up particles that have some interaction that attract them to each other. But we pin the spin down particles. You can think of giving them an infinite mass, and then calculating the effective binding energy as a function of the separation between the pin down, spin down particles. So if you want to read more about this, you can take a look at this PRL from 2017. So when we do that, we find something extremely interesting. So if we tune we considered 5 different interactions, and the energy of the dimers for each case is minus 1/40, minus 0.025 in lattice units for all the interactions. But we see a great difference between the effective interaction between the dimers for the different interactions. So first of all, let's look at the first interaction where the range of the interaction is 0, they're point interactions. What we find is that the effective potential as a function of distance is repulsive. We get this repulsive behavior like this. Okay, this is actually universal. This is something you can prove. I'll show you in the next slide, in fact. Now, when we take if you keep the interaction local and take the range to be 1 lattice unit, we immediately get more attraction. So the range seems to play an important role. In fact, we go negative over here. If we keep it local again and take the range to 2, we get much more attraction, in fact, here. Okay. Now, if we take the range to be 2, but we make it quite non-local, we actually lose a lot of this attraction. So this is a non-local interaction with range 2, but we lose that attraction. But if we make the range 2 and then make it non-local, but make the local part strong, we actually can get this attraction. In fact, we can get even more if we make this even stronger. This interaction, in fact, has a repulsive non-local piece and a stronger local part, and you can see the tail is even stronger here. So we followed up on this with a paper, Yoshiko and I did the study not too long ago, where we went back to this dimer-dimer system, and we solved it exactly, where we pinned down these particles, these downspin particles, giving them infinite mass, essentially. And then we did an exact calculation. So if you pin down 2 particles, and we take the zero range limit for the interactions so that essentially we have delta function interactions. And for the one-dimensional case and the three-dimensional case, we solved both cases. And what you can do, because it's just two delta functions, you can get the even parity ground state, and you can get the odd parity ground state. And it's then the sum of those two energies that you get for the binding energy of the total system when you bind the whole four-particle system. So when you add the even and the odd together, you get an effective repulsive interaction. This is the exact result here in the red, and then in the dashed line, you see the approximate frozen dimer approximation that does a good job for the long-range behavior. You can do the same thing for the three-dimensional case, and you again see you get universal repulsion. In fact, this is something that's well known, that if you have a zero-range interaction, if you have two dimers, they repel each other. And in fact, the dimer-dimer scattering length is 0.60 times the particle-particle scattering length, whereas the particle-particle scattering length was positive because there was a bound state, and it was actually an attractive interaction. The dimer-dimer interaction is positive, has a positive scattering length, but is repulsive. It doesn't have a bound state. Okay, so then we took a look at what was going on in more detail. And we did some calculations using the generated coordinate method. These are calculations that Yoshiko did. We looked at the deuteron-deuteron effective interaction for spin equals to 2. Essentially, what we're doing is we're lining up the spins so that they both point in the same direction, such that now we have some Pauli repulsion that's occurring as a result of that. Okay, and so what we see here is the kinetic energy, okay, and then we have the potential energy. You add them together. The red solid lines are the total energies. And so what you see again is this repulsive behavior between the deuterons, okay? So we get this repulsion. We do the same thing for the spin 1 case for the tritons. Again, we are aligning the spins such that now there's quite a bit of Pauli blocking that's occurring, okay, even from the protons in the triton. And so we get a repulsive interaction. What's interesting is that for the alpha-alpha case in the S wave, we have, again, the repulsion from the Pauli blocking the kinetic energy. We have more attraction, though. And what we see is that we get an effective attraction here. And here's a key point. We get an attraction at about 3 Fermi. So if you think about 2 alpha clusters with a radius of about 1.4 Fermi each, when they kiss each other, the centers are about 2.8 Fermi apart. So we see attraction at around the point where the alpha clusters touch each other. So it's almost like a kissing interaction there. But if you go too far in, you get repulsion. If you go too far out, it disappears. Now, we can also look at the effective interaction between clusters for the deuteron-deuteron for the S equals 0 case. So now here we don't have the Pauli blocking, so we have a very strongly attractive interaction as a result. And we can also make the protons not point in the same spin direction, and then we get attraction for the triton-triton case for spin equals 0. Okay, so that's sort of a picture of what's going on with these effective interactions. Now, let me jump to some calculations we did quite recently for 2 different lattice spacings at leading order in a very simple interaction, but it surprisingly does an excellent job of reproducing all of the low energy states of carbon-12. So here are the lattice spacings of 1.97 Fermi, 1.64 Fermi. We're about to do 1.32 Fermi as well and improve our interactions. We actually have made a tremendous amount of progress on this so that we have gone up to, we can do calculations up to N3LO and chiral effective field theory with a fairly small lattice spacing now. But you can see that we reproduce the ground state, the first 2 plus state, the second 0 plus state, the second 2 plus, the second 2 plus state, the 3 minus state, and so on pretty well. And let me show you some of the structures that we're seeing from these calculations. So this is we're trying to confirm or reject what we'd seen before in our older work. And so we did some different alpha cluster initial states, once again, some compact triangle, as well as this bent arm configuration, S1 and S2. We did then, for the spin 0 channel, or on the cubic lattice, an A1 plus channel, we did a couple channel calculation and we found two states corresponding with spin equals to 0. We saw a ground state and something consistent with the Hoyle state. And we did it for different widths of these alpha cluster configurations, and they all give the same sort of result, that we see a very strong signal for this couple channel calculation with these configurations. With different configurations, we can also see them, but the signal is much weaker. Now, we also did calculations using shell model initial states, again, a couple of channel calculation. In this case, we're using shell model 2-particle 2-hole states, okay, elevating these P3 halves states up to the P1 half shell, a subshell. And so we again see that for different harmonic oscillator widths, we get a strong signal, and this seems to be corresponding with our third 0+ state. So we see a good overlap there. Now, we also did the same calculations for the 2+ states. And so again, we took a compact triangle, but in this case, we found the strongest signal for this chain more like this. We also can see it with this configuration as well, but somehow the signal was strongest for this case. This probably is lattice spacing dependent, so it depends a little bit on the lattice spacing as well. But we saw a strong signal for the first 2+ state as well as the second 2+ state in this couple channel calculation. Okay, so let me now just summarize. After a short introduction to lattice effective field theory, I talked to you about local and non-local interactions and the importance of the range and locality of nuclear forces on nuclear binding. Then I showed you evidence that nuclear physics sits near a quantum phase transition and consider the effective interactions between clusters. And I concluded with recent calculations of nuclear clustering in the spectrum of carbon-12. Now, I just added these things today after some of the discussion. There was a bit of discussion on how to think or conceptualize nuclear clustering in states that are not near threshold. So this goes back to Martin's question to VTech. So one way to think about this is to try to understand how this clustering picture sort of breaks apart or no longer holds when you have a deeply bound state. One way to think about it is to measure cluster entanglement. So what we did was, in this paper here from 2017, we calculated the short-range correlations, sort of what's called the contact, if you want, the short-range correlations for 3 nucleons in some close proximity to each other, or 4 nucleons in some close proximity of one another, and measured the signal for this 3 nucleon short-range correlations or the 4 nucleon short-range correlations as a ratio of the same object for the alpha cluster, for the alpha particle. Okay, so if we had perfect alpha clustering, we would see then 1, 2, 3, 4 for these nuclei with 1, 2, 3, or 4 alpha clusters. But what you can actually see is that at this resolution scale of about 1.97 Fermi, at that distance for the correlations, we see that the clusters are overlapping with each other, and we actually see a stronger signal than what you get by just counting alpha clusters, because the alpha clusters are entangled with each other, and you cannot say that one nucleon belongs to this alpha cluster and not that alpha cluster, but they're actually overlapping. So that's one way to measure these things in more deeply bound nuclei. The other question is about the geometry of alpha clusters. How could you actually see a tetrahedron or see a triangle in a given nucleus that's well bound? Well, one way to do it is to use a proxy. For example, you can measure the correlations of spin up protons. So we did this for some of the even carbon isotopes. And we measure the correlations of 3 spin-up protons in these carbon isotopes. So what you do is you find the positions of the 3 spin-up protons, take the longest leg of that triangle, and then make that scale that to 1 lattice or 1 in length, and then try to figure out the location of the vertex of that triangle. And you can see then this geometry that you get out for carbon-12, carbon-14, carbon-16. Okay, so I know I've reached the end of my time, so thank you very much for your attention.
Thank you very much, Dean. If we have a pressing question, please raise your hand or enter it into the chat. Try to look at both. Sorry, someone had a Grisha.
Yeah, thank you. Very enlightening, Dean. But could you please again explain this picture? I didn't quite. This is the one that, yeah. What probability we're measuring here again?
Yeah. So we find 3 spin-up protons, okay, and then we have now a triangle because any 3 points in space form a triangle. And then first we find what is the longest leg of the triangle, and we scale that down to 1, just so that we can draw a pretty picture of the distribution. Okay, and then we rotate the triangle such that the longest leg of the triangle is on the x-axis, and then the third vertex of the triangle is in the xy plane. And then that is the probability distribution of where the vertex is. So you can see we have a predominance of acute triangles that we're getting from this configuration. We're not seeing, for example, lots of points here where we get an obtuse triangle, which is more like a bent arm configuration. So that's what's being shown here.
Okay, I see. All right. Beautiful.
Okay, I think there's several things to return in a later discussion on this talk. So let's see, he's released the scheme. So Yasid we'll talk about the beta delayed proton emission in boron 11 that was mentioned actually in Marek's initial talk, and or maybe it was Vitek's. So Yasid, are you?
Yeah, I'm here. Can you hear me?
I can hear you, but I don't see your screen.
Just because I'm not sharing it. So right now.
That's good.
Okay, so. Okay, so I'd like to thank the organizers for inviting me to give this talk. This is about an experiment we performed with the ATTPC active target from the NSCL to observe the decay of beta delay decay of barium 11 with proton emission. So I will talk about the experimental evidence and also future developments. This was obviously there's a clear motivation to study this from the low energy nuclear physics standpoint, but there's also some bigger motivation that links together other scientific disciplines that could be well, nuclear structure, but also dark matter and neutron lifetime, which is great, even though it's, of course, this is a very exotic scenario, but at the same time brings visibility to other communities about what we do. And if they are successful, they help to constrain further our models, of course. So as a matter of, as a proof of that this is still an ongoing topic, there was an experiment like a couple of weeks ago about this type of decay that I'm going to explain in GANIL, but on helium-6. So the thing is that the decay of the barium 11 is linked somehow to the problem of the neutron lifetime that probably you know very well, which is that, well, it's related to the free neutron itself that undergoes decay into a proton. So 2 types of different experiments. And actually, this has been measured many times, and this is still a long-standing problem that these 2 types of experiments, what we call in beam and in bottle, yield different results in the sense that they're within the 1%, which is 4 sigma away, they do not agree. And as I said before, this has been measured. There are a plethora of experiments and models going on. So one could think that there might be some stupid mistake that they are doing in the measurement of this. That's indeed a possibility because everybody does that. Or there may be some different observables, measuring different decay modes, or something that we have not observed. The thing is that, well, this is a long-standing problem that's still going on, and this was also linked recently by Fornal and Greenstein to another exotic scenario would be, okay, so why we cannot imagine a scenario where the neutron, that free neutron, let's say like this, decays into a particle, a dark sector that we cannot observe, okay? And this would be something like 1% of the time. That would explain why we see the difference between these 2 models, okay? So in particular, they mentioned that, well, this could happen in nuclei. So that brings everything to our domain with neutron separations energy below 1.572 MeV. And well, in this paper by Futhner and Riesager, there's a list of possible candidates where this dark decay on nuclei could be observed, especially the neutrons in particular. So among all of them, the beryllium-11 is the best candidate. And that would lead to a decay into beryllium-11 into beryllium-10 plus an unobserved particle. And the branching ratio, as you can see in this plot here, would depend very much on the mass of this particle, okay? So now if we think about why beryllium-11 it's special about this, it's because, well, it fulfills those requirements because it's a halo nucleus, and this is where it becomes interesting for us in our domain, because this type of decay would bring, well, it's competing with other open channels on beryllium-11. This is literally the aim and the goal of our experiment. So this type of halo nucleus, as we know, it's where we can think about a decoupled core and an orbiting neutron that can be treated independently. So what will happen is that one of the competing channels will be that the neutron may decay into a proton and into the boron 11 daughter and above the binding energy, and it will emit a proton. And the reason this is special, because that would lead to some channel that will be similar to what we would expect from this dark neutron decay, let's say like that. So let's focus on what we can measure in our case, which is the beta delay proton emission, which is a counterintuitive decay because boron 11 is a neutron-rich nucleus, and that means that we are observing proton emission from something that tends to get more stable by emitting neutrons, right? But this is possible if we fulfill this condition, which is that the neutron separation energy is of the order of 0.782 MeV, which is the case. And also that means that the Q of this beta delay proton emission channel is quite low. It's narrow. It's of the order of 280 keV. So what that means that we would expect protons of at least the maximum energy of 280 keV. And well, this would be the cartoon depicting what we would expect to happen here. There was a very first attempt to measure this decay by Riesager and collaborators that was done by implanting beryllium-11 in a catcher and let it decay. And of course, the way you analyze that is bringing your sample to an AMS and, well, analyzing how many beryllium-11 you have. So this is kind of a passive technique in that regard. And they deduced quite a high branching ratio for that particular channel. But one has to say that this means that that would be all the channels leading to any residue that would be together with beryllium-10. That means proton emission, and of course the hypothetical dark neutron decay, okay? And that would happen in the case that we'll have an unobserved resonance, which is, of course, well, one would expect this type of near threshold resonance of, we can see here that will be, well, depending on the energy of the resonance and the branching ratio, one have one shape, and of course different, well, different energies and different branching ratios. And of course, the other possibility is that there's an unknown branch. So there's beryllium-10 because it's the residue of some unknown or unobserved decay. So the thing is that, well, as I said before, they measured all the channels. So the idea or what we propose is to measure specifically directly the decay into the beta delay proton emission. And well, by comparing those two results, we can infer or rule out, let's say, if there's a kind of like a dark decay. But even more important for us is the fact that we will learn a lot about the nature of the halo of beryllium-11 by measuring the proton energy distribution and, well, all the observables that come with that. Of course, this is a very challenging task because one has to measure very low energy protons. So what we did is we used an active target, as was mentioned before. And the scenario is quite complicated in the sense that besides the proton, there's also another dominant channels. But in any case, this is the probably one of the best technologies that we can use it's an active target time projection mode, which meaning that we don't do the reaction, but we observe the particle that we implant decaying into the gas. Okay, so we did the experiment in Triumph. So we implanted beryllium-11, and this gives the TPC itself gives a lot of efficiency, and we can reconstruct protons and other particles coming from other decaying channels, I will explain. And we try to minimize the struggling of the particles that were decaying the gas, because this is one of the things that kills you, literally, in the sense that you are dominated by struggling at very low energies because of the Bragg curve. No matter what you do, that you have to reduce it because that's nature and there's nothing you can do to minimize the struggling. So that's one of the biggest problems, and I'll show you. And the other problem is that the beryllium-11 is not fully neutralized, so it drifts once you implant it. Okay. The aim and the experiment was designed to measure these protons of around 180 keV that leave tracks of the order of 10 centimeters, which are long enough to be identified. And this is what we observe in a calorimetry mode. Calorimetry mode means that we just collect the energy of all the particles that are stopped in the gas, or we believe we're stopped in the gas, by observing that the track does not punch through. And we observe, of course, the dominant decaying channel. It's into the lithium-7 plus alpha, or the ground state of the lithium-7, or the possibilities also to decay into the lithium-7 excited state plus the alpha from the boron-11. That's the one that we want to measure is the beta minus proton, and everything would fall into that energy region. We also downscale this part in terms of trigger to have some calibration and, of course, some way to normalize for the branching ratio. So, but in any case, we observe several contributions coming from one single particle, because the particle decays from the cathode and only one can be observed most of the time. Otherwise, you observe both decaying in the gas. The key of this experiment, or at least I want to believe that this is one of the most important parts, is to measure how the response of the detector to those protons are, because otherwise you are literally blind to identify the particles in this region where it's dominated by tails and lithium-7 in this case. Okay, so we implanted protons in the TPC to have the response function, which luckily for us, it's quite different from what we want to identify. And one thing that it's challenging at which the active targets or gas detectors in general excel at low energies, that they provide much better energy resolution than any other detector that like could be, for example, a silicon detector. So this is what we observed. And here what we did is just a simple Monte Carlo analysis by comparing the reference curve, the one from the proton that we measure, and of course the one from lithiums that we have a lot of them, and it's easy to identify. And we also compare that with parametrizations that exist in different, well, we have SRIM, or we have these databases that are available online, and all of them agree pretty well. So we can clearly distinguish between, at least at the largest energies, between protons and lithium-7 and alphas. That's as we'll show later, because those are the dominant particles, or the particles that we observe with more frequency here. So the plots are very different, the feeds are very different, and we compare essentially the result of the feed between both to obtain what you observe here, which is the energy distribution of what we believe are the protons that we measured with this method. So this was the first observation of this beta minus proton emission, and the branching ratio agrees with what was established before by the calculations by Risager. And now, of course, the problem is that this method can be improved, and it will be improved, I hope. We have an uncertainty of 30%, which is quite large to deduce anything about the hypothetical decay. But in any case, what we observe, and it's really relevant for us, is that, well, this decay happens through a narrow resonance of the order of 12 kV. I think that this number is wrong, but it should be of the order of 15 kV or something like that, in beryllium, in boron-11. So it's less exotic than one would expect, but well, it's still something with very low branching ratio. And these are the parameters from the resonance. And if this happens like a phase space decay, our calculations show that the branching ratios will be shorter. Of course, the theory tries to replace the result, and as often happens with this type of difficult measurements or controversial, if you know, there's things in favor and things against that. So there's there's some calculations that that agree with the near threshold proton emitting resonance in boron 11. There's even an ab initio calculation that has not been published. I don't know the state of this, but the last thing I know is that, well, there were some very positive results regarding that. And also there's from the shell model point of view, there's also, negative or calculation that, says literally that it's the branching ratio that we measure cannot be real. And this opens a scenario where one could imagine that this decay may happen from the isobaric analog resonance. That's a long tail that, it leaks literally like that into the region that it's constrained by the Q value of the beta decay. Okay. And of course, we had criticism on our experimental procedure because, not just 2 months after that we published our results, there was other publication saying that the particle ID that we use is not reliable, and there was also some criticism about the GT, that it was too high for that. Although regarding this point, I want to say that we have a very large uncertainty in that regard. So because of this, we decided to reanalyze the whole data, including other particles that, for example, tritons, even though the probability of having the beta delayed triton emission is very, very low, what we did is including all the possible particles that could be there, regardless the branching ratio, to reanalyze the data. Well, this is what I want to show you here is not the perfect fit that you would put in a paper, but some kind of borderline fit, because it's true that at low energy, it's when the straggling effects become so difficult that makes the identification really complicated at this point. So what I want to say with this is this: obviously this is not a perfect experiment that can be improved, and with our honest opinion, this is what we believe we observe. So just to summarize this part and almost to conclude, as well, we have this new particle ID, and one of the criticisms we obtained, we got, is that the chi-square test that we used was not properly done. We did it according to the criticism, and then we obtained more or less the same result. And well, these are just details about the analysis that, well, if someone is interested, I could share them, but I'm not going to explain them here. And well, we are preparing a long publication explaining all the steps that we did for the analysis. And now the question is, what could we do regarding this type of measurement? And of course, the only thing that we can do is to measure more and better. So the next thing that we are going to do, and I'm excited to say that this will happen next month, we are going to measure that resonance directly. So we developed that very low energy beryllium-10 beam as an SEL, RIA3, and we'll do just a simple resonant elastic scattering at forward angle where the resonance is expected to appear. And well, we'll see if that's true or not, but this will complement the measurement, of course, which is something that it's very much needed. And the second thing is that we are also developing a new optical TPC for high resolution measurement of the recoils of beryllium-10. This is, of course, a more general development, but the idea is to improve the measurement and have a more clear design of the experiment to repeat it somehow. And in the hypothetical case that there's some recoil emitted with a particle that cannot be detected, we have the idea of doing that. of course, that also brings other possibilities, like, for example, doing beta delayed neutron emission studies where you only measure the recoil. And this is already ongoing. We have a detector prepared that can measure 5 kV electron tracks, as you can see, with an optical TPC, and nuclear recoils too. So this is something that we'll test in the future. And well, that's a conclusion. I would say that, well, this is an experiment we perform, and we observed emission of protons from beryllium-11, and we used a particle ID based on the characteristic energy loss curves for all the particles that we believe what we measure there. And we have analyzed the data with 2 different methods that provided and yielded very similar results. And well, we expect to improve our experimental setups for new measurements and complementary measurements too. So thank you very much.
Thank you. Are there any burning questions for Yasid? Grisha, you have one.
Yeah, thank you, Sid. Exciting results. But my understanding is that for this 12 kV width implies a single particle state, right? Essentially single particle state. And wouldn't it be observed nicely in DN reaction on beryllium-10, for example? Is there such data? Have you looked into that?
I think that there's some effort going to observe that, but I think that one of the things there is that, if I'm not wrong, you need a very good resolution measurement for that, because obviously it's in a region that it's really populated with a lot of states. And of course, one of the things is what's the spectroscopic factor for that. Obviously, if you do resonant scattering, that's what you expect to have the better overlap with what this type of measurement, right? So I don't know what's the state of that. I know that there were some groups trying to measure that. That's for sure.
Yeah, but the spectroscopic factor should be large, right? Because the width is the partial width is very large based on your results. So it should be single particle state, shouldn't it be?
It should be large, or well, yeah, you are right regarding that.
Right.
But I really don't know if there's it has been observed right now.
Oh, okay, I think we're going to have to take the rest of this discussion until the end. Yasid, I want to prime you with a question for later. In your initial paper, I was stalled when I hit your log FT, which seemed to be too small to be plausible. And maybe in our discussion, you can explain why it can be a unit lower than super allowed. At least that was the number I got from the original paper. Anyways, okay. subject for later. You can explain that to me. And
okay.
All right, we don't have time. We'll come back to it.
All right.
Okay, so on to reach the scene. Great. So on to our last talk. And Valerian, can you take the screen? Valerian Alcindor will talk about this famous fluorine 15 case that was mentioned at the beginning of the session. So take it away. Got 20 minutes.
Okay, so you see my screen?
Yes.
Okay, very good. So yes, so yeah, I'm Valerian Alcindor. I'm a postdoc. I'm currently working at the Institute for Kern Physics at TU Darmstadt. But today I will talk to you about results I obtained during my PhD, which was about the study of fluorine 15. So yes, fluorine 15 has been already discussed a little before. Just I want to start with a very simple reminder of where fluorine 15 is located. So as you see, it is an unbound nucleus located at the proton drip line, and it is 2 neutrons away from the proton drip line, which is rich already for fluorine 16. So with this in mind, let's say that you would expect to measure fluorine 15 as a broad resonance. And the first assumption, which I think was already discussed before, and it's not the case, is that you would expect to have some kind of an increased width as a function of excitation energy, and this is what you would obtain by doing a simple calculation of the Wigner limit. But if you look at the results for fluorine 15, you see it is clearly not the case. It is totally not true. And you see that between the ground state and first excited state, you have around an order of magnitude narrower widths. So this is in fact linked to this is linked to the structure of this state, so which was studied here and measured somewhat recently by Florence de Grosse and collaborator, published in 2016, where they measure this 1/2 minus state. And the structure of this state was mostly understood as the one of the nitrogen 13 plus nitrogen 13 core plus 2 proton, because as you can see, it is just at the position of the 2 proton emission threshold. Also, if you think about the fact that the width is narrower, then you can expect for this state to have a longer half-life. And due to that, we saw that it could be possible for this state to decay by emitting a gamma rays to the ground state. And this would be an extremely interesting result, because gamma emission between unbound state has not been measured often. Then also it would be an E1 transition from this narrow state to a broad ground state, which would mean a broad gamma energy. So this, of course, has been presented multiple times, so I'm not going to give too much detail about it, except to say that this effect of nearby threshold is quite important, and that, of course, here you have the very famous Hoyle state. So in carbon 12, where you have this 3 alpha cluster structure just nearby the 0 plus, so 3 alpha particle emission threshold. And this led to many work and this famous conjecture of Ikeda and collaborators that the structure of states near the N-alpha decay threshold should lead to the formation of N-alpha cluster states. And again, this has been extensively discussed already. And then one can ask themselves, can we generalize this Ikeda's conjecture? And again, this has been also presented before, but here, of course, you see that you have carbon 12, you have lithium 11, which is a very famous halonucleus with a core of lithium 9 surrounded by 2 neutrons. You have boron 11, which was presented just before, and you see that fluorine 15, despite being also with 2 protons and not neutron or alpha states, seems to have the same behavior. So I think it's interesting also because it has been discussed a lot for neutron, but can we generalize this also to charge states such as for proton? Other motivation for studying fluorine 15 was the recent prediction from Canton and collaborators and Fortune and Cher, which both predicted that there were other states at higher excitation energy, 5 alpha minus and 3 alpha minus states. And one here interesting thing is that you see that the energies are quite different between the two predictions. And particularly one of the interesting disagreement between the two predictions was the width of this 3 alpha minus state, which is an order of magnitude narrower in the prediction of Canton and collaborators. So as a summary of why we wanted to measure this, to perform experiment on fluorine 15 was, first of all, we wanted to measure these negative parity states. First, confirm the energy and width of the 1 alpha minus state, as well as measuring these 2 new states. And the idea was to use resonant elastic scattering reaction to do so. Also, this state, this 5 alpha minus and 3 alpha minus, are located well above the 2 proton emission threshold. So one of the interests of our experiment was to study the 2 proton decay from this state, which could be either direct to nitrogen 13 ground state or sequential through oxygen 14 first excited state. And finally, as I said just before, we were interested in trying to measure the gamma balancing ratio from this 1 alpha minus state to this 1 alpha plus ground state. So as I said, we used the resonant elastic scattering reaction, especially we used here the SIG target technique. And the idea is that as the energy of your incoming beam is going to lose energy inside of the target, the center of mass energy between your fragment and your particle is going to change also. And when you reach one of the states in your compound nucleus, you will see very nice resonances. And here on the bottom right panel, you have an example of such resonances where you have this Rutherford scattering, so continuous cross section here. But once you reach a state in oxygen 15, you have a very clear resonance. And one of the interests also of such a measurement is that the energy, width, but also spin and parity is going to change a lot the shape of the resonance. And here you see, for example, that it is not a simple Breit-Wigner resonance. You have interferences which give a lot of information on excited state. Then, as I said, we were interested in fluorine 15, so we use an oxygen 14 beam of around 7.5 MeV, and we used several thickness of target to populate different states. The first and main target of the experiment was a target of around 100 micrometer, with which it was possible to populate state between 7 and 4 MeV in the center of mass. So we could measure the 3 minus, 5 minus, and again the 1 minus state. Also, since we were interested in seeing if there was some gamma emission from the 1 minus state to the 1 plus ground state, we used another target which was of a smaller thickness of 70 micrometer, with which the 1 minus state was not directly populated. And we also used a thick target with which we could measure the full excitation function to remeasure also this 5 plus state, as well as give some point for verifying our calibration. So yes, as I said, we did, in fact, 2 experiments about fluorine 15. The first one was performed in May of 2018 in Ganil at Leeds. It was part of the same campaign as the experiment of Shumpei. We used also MUS2 detector, but in our case, we were only interested in the 0 degree measurement. So we used the MUS2 detector, which were measuring angles between 0 and 5 degrees. Also, since the detector was at 0 degree, we protected it with a 34 micrometer tantalum foil to stop the beam. And this detector was composed of 2 stages. One was a 128 strip DSSD, both X and Y, and another one which was a 4x4 CSI crystal array. And then we performed a second experiment, this time a more, let's say, complex experiment, which was the first experiment of the MUGAS campaign, if we don't consider the commissioning. So in this experiment, we used the MUGAS detector, so only the front detector to detect the proton, which correspond in fact to the MUS2 detector. We used the Agatha high purity germanium gamma ray detector to detect the gamma, and the VAMOS spectrometer to measure the recoil of nitrogen 13 and oxygen 14. What is very interesting with this setup was that it gave us the possibility to measure the full kinematics of both the 2 proton and gamma emission. And this is the results we obtained. So here it's a compilation of both experiments. What you see in red are the results that we obtained. So the resonant electric scattering measurement of the first experiment. And in green, you see the result obtained, so the total cross-section we obtained in the second experiment using the missing mass method. And in blue, you have the previous result from De Grancey and collaborator, and in black, you have the R matrix fit. And what you see here is that we were able to assign with not any issues the 5 minus state, but we had an issue for this state, which was consistent in the R matrix fit both with the 3 minus and the 1 plus state. But as I said here, in the second experiment, we were able to measure the full kinematics of the reaction. And with this, we studied the correlation and the decay mechanism of this 2 proton emission. And what we saw is that for both states, this 2 proton emission was sequential through oxygen 14 first excited state. And here you see that especially for the higher energy part, above 6 MeV, which corresponds mostly to this 3 minus state, you see that very clearly you have a nice representation of this sequential decay. And then if you look especially at this spectra, you can know from this which is the second and which is the first proton. And by combining the measurement of the second proton with the measurement of the recoil of nitrogen-13, we were able to reconstruct the intermediate state of oxygen-14. And then we were able to use derive the center of mass angular distribution of the first sequentially emitted proton, which you see here. And by fitting it using Legendre polynomials, we can clearly see that it is only consistent with k = 2. And by combining this information, because it would be either 3½ plus or 3½ minus, and here that it's either 3½ minus or 1½ plus state, we could assign without any ambiguities the spin and parity of this state. And here, finally, these are the results that we obtained in this experiment. What you see is that for the previously measured 5½ plus and 1½ minus state, we have a very good agreement with previous experiment. And especially interesting, you see that for this negative parity state, they are all observed to be quite narrow. And this is especially interesting because they are well above the Coulomb barrier. Now, if we go back and if we compare our results to the predictions that I've shown before from Canton and collaborators and from Fortune and Scher, what you see first is that we have an almost perfect agreement with the energy calculated by Fortune and Scher, while the results are much more different from the result of Canton and collaborators. But if you look in detail, and especially if you look at the widths, you see that it is not true at all. We are an order of magnitude narrower than the prediction of Fortune and Scher. And by just scaling the result from Canton collaborator by this value, which is like reasonable compared also to more recent predictions they did, you see that in fact we're in very good agreement with what they propose here. And one of the possible explanation could be also again a proximity to a threshold, and this is still let's say under discussion at the moment with the expert from the Gamow shell model. But maybe similarly, and here it is just a qualitative in this case, similarly to what we see with the proximity between the 1½ minus state and the 2 proton emission, you see that this state is also close to the 3 proton emission, which might have a large impact on the structure of this state, compared to, of course, the carbon-15 mirror nuclei, where, of course, there is no 3 neutron emission threshold nearby. And now, finally, just a quick word about the gamma decay, because as I said, at first it was one of the, maybe the main, let's say, reason for performing the experiment, because such gamma decay is extremely interesting. But here, as you can see, you have the center of mass energy as a function of the gamma energy, and you see clearly that there is, in this area where we would expect to see some events, there is no events compatible. So with this, we were able to get a limit, an experimental limit, and we finally understood why fluorine-15 was not a good candidate. And this was due mostly here to the spatial distribution of the 1/2 wave function, so radial wave function, which was totally overestimated in our first assumption. And by doing the calculation, we find, in fact, a result which is very consistent with the experimental limit. So as a conclusion, I would say that in the first experiment, we were able, with the resonant-elastic scattering reaction, to measure and confirm the properties of the 5½ plus and 1½ minus states. We also performed a precise measurement of the new 5½ and 3½ minus states, which were found to be very narrow, despite being 3 MeV above the Coulomb barrier. We have some interpretation which are on the way, and that will be presented in the paper that we will submit soon. And also, we were able in the second experiment to study the correlation between the fragment and the protons, and between the protons using Dalitz plot. And they showed that the 3½ and 5½ minus state both decayed sequentially through oxygen-14 first excited state. It was also very helpful in assigning the spin and parity of the 3½ minus state. And finally, concerning the gamma branching ratio, we were only able to determine an upper limit and we understood by calculation why we did not measure it experimentally. But I think it gave us some insight on what would make a good candidate for gamma transition between unbound state, and maybe also we can learn from this. So yes, thank you for your attention.
Thank you very much, Valerian. Questions in chat or raise your hand?
I see two ends.
Okay, maybe I'm favoring Grisha here, but he just happens to be on the top of my list. Hold on, let me scroll down to see who the other person is. Give them a chance. I don't.
There's only one hand. Maybe Gregory raises two hands.
Yeah, it's Gregory who raised two hands.
Okay.
Sorry.
Grisha, what's your question?
No, it was one hand, but so I have two, but they are short, I hope. So the scaling that you've done from theoretical calculations, it looked like after scaling, the width has not changed, because on the previous slide, I think you had this 3½ minus state much higher, and yet width was the same, 40 keV. Yeah, this, right?
Yes, yes. Okay, so
is it typo or I'm...
No. This is just a very let's say qualitative scaling for my part as an experimentalist. It was just to see if just scaling down the energies of quantum collaborators, we are close to our experimental results. I don't think there is much let's say a theoretical value, especially for this. Which I guess, of course, should also change.
Yeah, it would get better, right?
Yeah. So this was just because also recently they published a paper with many states with states that could make sense, and also they were able to reproduce much better this ground state, because you see here that it would be better here. So it was more a qualitative way to say. Maybe by changing the potential or something, they could match better our energies, and that okay, obviously you're right. I think the width should also change and get better. Yeah.
So, and have you compared this partial widths that you're getting with the spectroscopic factors for carbon-15, the mirror nucleus? How do they compare?
So the only thing I didn't calculate it, the spectroscopic factor for also carbon-15. It's just here what you see is that yes, this is around 4 times larger in carbon-15, which was one of the, let's say, strong argument from Fortune and Cher on saying that quantum collaborators should be wrong, because there is such. I mean, he said in his paper, and I think I oversimplify it, but that. It cannot really be that the state is going to be much narrower in fluorine-15 than what is seen in carbon-15.
Yeah. Can it be that it's actually different 3½ minus state, because they are completely different states, appears?
Yeah, the structure could be very yeah.
So can it be different 3½ minus?
Yeah. Also, this is still for me, I mean, very qualitative. I see it's the same level sequence, but yeah, it might be that it is another 3½ minus state. I don't know. I don't think there is much possibilities.
Yeah, because the discrepancy is very large. It cannot be the same state, right? Or measurements of carbon-15 are wrong, or something is not.
Did Fortune calculate only one 3½ minus?
If I remember correctly, yes. Yes. Because above it was more. No, I think it didn't calculate the positive parity state. So yes, I think he only calculated these two negative parity state above this 1½ minus. Yes.
Yeah, there's a candidate for 3½ minus at 6.3 MeV, but maybe it's too high.
In carbon-15, you mean? Or
yeah, in carbon-15, yes.
Yes. But do you think it would match? Because here,
no, maybe it's too high, but I said that there's something there.
Okay.
Okay, so we're now, excuse me, we're now into our overall discussion time. And so there are a few questions that came up that were not they were either just entered into the chat that we didn't talk about at the time, or that came up that we short-circuited some of the discussion on. And the first one, actually right at the beginning, Olivier asked, could we discuss that most of the effects of the reduction of the nucleon-nucleon interactions and reduction of spectroscopic factor values could have been anticipated right from the start for weakly bound systems. Basically, we're over-influenced by harmonic oscillator wave functions and should have seen these problems with even Wood-Saxons right from the beginning. That's a paraphrase. Olivier, do you want to say some more?
No, that's okay. I wanted to know if there's additional things that are brought by the continuum shell model as compared to the a simple hand waving extension of the radial wave function in unbound systems.
That might be for Marek or Vitek.
Well, you know, as you said, if in the systems that are close to continuum, you have to include continuum. Otherwise, you just make still the bound state calculation, then Wood-Saxon is not changing that. So if you have a two-particle interacting, you must have the two-particle completeness by putting nucleons in the bound, in the discrete and in the continuum states. And that is what determines the actual value of the nucleon interaction, or sort of indirectly through their contribution to the energy.
Well, there's an example there are two actually examples we did experimentally. We studied odd nuclei, like the things you were showing, like in odd nuclei where you have the neutron that is, for instance, unbound, and the proton that is deeply bound, and in which you have you expect to have a reduced proton-neutron interaction as compared to systems where in which protons and neutrons are almost equally bound. And with simple calculation, we can find this reduction just looking at the extension of the wave function and doing the overlap between the wave function of the proton and neutron. We can find the right order of magnitude already this way. I mean, it means that it's an effect of continuum, but I was thinking that if there are effects beyond this simplified approach, you were talking about imaginary part of the interaction.
Well, you cannot, in the language of gamma shell model or also SMAC, if you are describing the unbound state or weakly bound state, the two-body matrix element may contain the imaginary part, and this is something which is expected and it exists. So I think this kind of simple arguments based on the property of the discrete state, which is coming to the threshold, is certainly an important part of the effect, but not everything.
So let me make a comment. In his famous paper, Fano, you know, many years ago, was talking about the change of interaction due to the coupling to the continuum, right? In his first configuration interaction paper, which launched, you know, the whole program of continuum shell model. So this has always been a very strong motivation to the people, you know, trying to develop those models of nuclear structure and reactions. Your question, you know, can we get some easy signatures of the interaction changes, right? as one approaches the continuum is a very good one, you know, and I think that it's, you know, it's a very complex, of course, problem. How to be sure that the effect is just due to, you know, some change of some term of your effective interaction. But this is extremely good question. Yeah.
Well, at least there are some data. We made this especially to test this. So there are some nuclei on fluorine 16 that was done by François de Oliveira, fluorine 26, and we also demonstrated the isospin dependence of this proton-neutron interaction. So as a function of the change of binding energy between protons and neutrons. So if you could address this,
but
maybe we can learn a bit more. Yeah, sorry.
I have a question. We have to define what you mean by effective interaction. Okay, if you mean, you know, say some shell model matrix elements, okay, which are, you know, you have to change, you know, some numbers in your shell model code to reproduce the data. In reality, of course, you have true forces, right, between nucleons, and then you have to solve many-body problem and get wave functions. So I'm not sure whether thinking in terms of the matrix representation, okay, of the shell model is extremely useful in this context.
Yeah, I agree with you. It's just to give the change of the order of magnitude, but I'm curious to see if you can reproduce this data and what is the part coming into the imaginary part, and with a full description of it. Yeah.
This is good. I'm very happy we are talking about those things here.
Vitek, you mentioned in your talk that the history of the near threshold consequences from Wigner on into this paper by Barker and all. And there's two parts of it. One is a change in the structure of states due to thresholds. I don't think it's a deep question. It's multifaceted and all that. And I don't think there's a problem with that. And then there is another question of not just some relocation of strength, but actually an increase in the density of states. And I was challenged by actually one of your colleagues who was a disbeliever in that, and made an argument that there was no, that couldn't be supported by data, and thought, well, maybe there's some statistical analysis you can do. And then it turned out in my thought process that was really unprofitable, and you couldn't do it because you didn't know the energy scale. How could you make a statistical argument of relocation of strength if you couldn't fix how you were averaging it? I think you know who I'm talking about, who challenged me, but you must have this. Do you have this problem also, or do you just ignore it?
Well, the argument by people like Barker et al., right, is based on, you know,
Our matrix.
Yes, you know, so there are two things, right? First, you have the continuum, you know, non-resonant continuum, and you can define the level density in the continuum. So this can be done, the epsilon over dn, right? So, and this is totally generic, really not very dependent on the model. And then you have, of course, those states which are embedded in this continuum, which are of great interest to us, right? And they, you know, they also have their own level density. So in the language of SMAC, right? You know, you have those two parts of the Hamiltonian, the shell model Hamiltonian, which gives you the usual level density, and then there's the second term, which creates additional component to the level density, right? And what Barker showed, that this second term gives you this huge enhancement. So, you know, you are not going to go very far just by counting states, because you are not going, in this way, you are not going to consider the continuum contribution, right, to the level density. So let us be clear, this is not a situation in which I go very high in energy and I see many, many states. I see many states, but I have also non-resonant background, which also contributes, right?
Yeah, okay. We also had an unfinished discussion concerning the possibility of FMOF states in nuclear physics. And I don't know if someone wants to summarize that story. I'll provide a straw man that maybe Danielle wants to knock down. The beauty of the atomic cases are you see a hierarchy. You see the 22.7 excited state, factor of that much larger. And so it's clear what it is. It can definitely happen. It's on solid ground, that many body physics, because it's seen in that case. In the nuclear case, what are you going to see that is going to be revealing about the nuclear many-body problem?
So I think this is a really important question. So first I want to push back a little bit on the idea that the atomic physicists saw exactly 22.7. So you only see exactly 22.7 if A, you're in the limit of a zero energy resonance, and B, the range is zero, right? So even in the Grimm was not the first author on that paper, but the results of the Innsbruck group that you referenced earlier, Lee, even in that experiment, they don't, you know, there are range corrections, right? And so as I mentioned, right, one of the issues in nuclear physics is that the range corrections tend to be larger. But as you point out, right, the other issue is that you can't, or yeah, you'll never get exactly to the unitary limit where the resonance state is at zero energy. I did want to show this figure. Can I share my screen? Is that going to work? Let's see.
Should be able to.
Yeah, there we go. Okay, so Hans and I were chatting a little bit offline, and so I want to show this figure from a paper by Rupak and collaborators. I was not involved in this work. So this is what's being done here is to plot the binding energy of three-body states. So this is the binding energy of three-body states. It's converted to a momentum, but this axis is a proxy for binding energy of three-body states versus the binding energy, again, converted to a momentum, but again, proc of the two-body state. So the real world is here, and this state is the triton. So what I meant about sort of about uncovering the FMOF physics that is underneath in nuclei is that if you have a reliable theory of these systems, you can follow the trajectory of these states as you make the system, as you move the system closer to the zero binding limit. So if you make the deuteron shallower, then suddenly this FMOF state appears out of the continuum. And you can actually trace the pole as it crosses the threshold and comes out of the continuum and becomes a bound state. So this is exactly what I meant. This is in neutron-deuterons, the neutron-deuteron system in the three-body system. So the idea is that in the triton channel there would be an FMOF state if that was bound if the deuteron was bound by a little bit less, if it was closer to threshold. And if you lived right here at zero deuteron binding, then the ratio would be 22.7. But as you move away, the ratio is not 22.7. I mean, and that's a rigorous statement, right? That's not. So yeah, and so then even here, when this state disappears through, this is when the FMOF state goes through the neutron deuteron threshold, which is this dashed line. Even when that happens, you can still see its imprint on the phase shifts in the ND system.
So I see this as a way to understand or provide additional insight into the three-body system, I don't see an experimental challenge.
So I think what I would say is that so if you think about so let me take the other part of your question, right? You're absolutely right. You can't. It's difficult to imagine a situation where you're going to see 22.7 within error bars. But the other part of your question is it tunable? It's not tunable, but we have a lot of different two-body and three-body binding energies if you think about halo type systems across the nuclear chart. So that's what gives me hope that somewhere in the diversity of nuclei across the nuclear chart, you may find conditions that are favorable for an Efimov state, near threshold. Now, there's been quite a lot of discussion, for instance, in the context of systems like carbon-20 about what the experimental signatures of a virtual Efimov state would be. So like after this one crosses the threshold, what could you see in the continuum? Would you see enhancement of the dipole response? Would you see, what would the scattering observables look like? So other people on this call are probably more qualified to talk about that than I am. But for me, that's if you really want to see an Efimov state in nuclear physics, probably your best bet is to look for signatures of states that are near threshold in the continuum, which if the nuclear interaction was tuned a little bit, would have been bound Efimov states. Just because they're in the continuum doesn't make them any the less Efimov states. It just makes the signatures a little harder to see. I'm sorry, what were you going to say?
Well, you sparked a number of questions, Miguel.
Yeah, can I share my screen?
Yeah, let me stop here.
Because yeah, this one. So we wrote paper 2019 about the possibility of Efimov states in boron 19.
Mm-hmm.
So the motivation for searching in boron 19 was, so this paper was in collaboration with, do you see my PDF?
Yep.
Yes.
Yeah, so it was with Hiyama-san, Lathauskas, and Carbonell. And the idea was that this system, to our knowledge, was the three-body system with the highest scattering lengths. So of course you have the neutron scattering length, about 20 Fermis, and then the boron 18 scattering length is about 100 Fermis. And it's not very well known precisely. So the idea was, is there any value of the boron 18 scattering length that would make this system Efimov state? And so this 22.7 is for, I think it's for equal mass particles.
That's right. That's the other.
So for boron 19, so I will come. So for boron 19, somewhere in the paper, we said that, yeah, so here the factor would be 2000 for these three particle masses. And so the conclusion was that in order to see a first excited state, so an Efimov series of two, the scattering length of boron 18 would need to be of several thousands of Fermis. So even several hundreds would not be enough. So yeah, so this is something you cannot tune because it is what it is. But the conclusion here was that even in a system like this with three particles, so here you have the wave function of so this is the wave function of helium-6 that Hiyama-san calculated with a similar model, where you see the distance between the neutrons here and the distance between the two neutron system and the fragment, helium-4. And you see that in her model, boron 19 was even bigger. So you have a strongly clustered system. And you can reproduce the properties of boron 19 ground state even at the unitary limit. So you can take the scattering length to even to infinity. So I think it was this picture here. Yeah. So this is the binding energy of boron 19 as a function of the scattering length in boron 18, and you see that, well, of course, the binding energy is not very precisely known, but yeah, so this system is a very good candidate, but even for this system, observing a second state would be very, very unlikely.
But I like what you said. I mean, you said you had this comment there also I saw on the screen, right? That the universal features associated with ephemeral physics are clearly visible, you know, and in terms of what Grisha was saying, this is clearly a big state, right? I mean, it's like, so these are these
so
conditions.
You mean this
yeah, exactly. Right. Yeah.
So we have a very short range interaction that is acting at very long range.
Right.
Okay, this has sparked a lot of hands. Lucas, you want to chime in?
Yeah, so
and Miguel, maybe you want to release the screen. Thank you.
Done.
Yeah, so I just wanted to, I think Daniel essentially said it, right? But I think it's not necessarily right to insist on the, you know, second state that should be observable, but we should rely on the fact that essentially ephemeral physics means that the presence and the position of one three-body feature determines a whole bunch of other things. And these are these universal relations, right, that one can have. And essentially, we have an ephemeral state if, for example, let's just say the charge radius of the three-body state would be related to the binding energy in a particular way. And so that would be sufficient evidence for me for ephemeral physics in that system. And atomic physicists pay quite a lot of attention to these universal relations too, and it's a big deal for them too. And I think this is what we should rely on in the absence of Feshbach resonances in nuclear systems. And so that's just my my 5 cents.
Hans?
Yes, I have a comment on this unfavorable scaling factor of 2000 that you had, right? So what that scaling factor is depends on how many pairs are strongly interacting, and it depends on the mass ratios of these particles. And so you can pick unfavorable things. And now it turns out that the case that you have in 2 neutron halo nuclei, where you have one heavy particle and two light particles, is not the best one. So if you could find a system where you have 3 interacting pairs and you have 2 heavy particles and 1 light particle, then this can turn the other way around and you can get a very small scaling factor. So for all the experimentalists, I think that's not the natural system in nuclear physics, but if you can look for a cluster nucleus where you have 2 heavy clusters and a light cluster, then you can make some ground on the scaling factor.
Yeah, in the same, I think almost the same paragraph. So Lazauskas said that theoretically it would be more favorable to have 2 boron 17s and 1 neutron in terms of the mass ratio. So you had heavy light. But of course, then you have the Coulomb repulsion between the 2 boron 17. So it's, yeah, so in theory it would be better, but in practice it would not be. It would be some states in neon 35, I think.
Well, I think that's a tough challenge. Grisha, did you want to make a comment? Is your hand still up?
Yes, I would like to make a comment. So if we go back to tritium, there is an experimental evidence, maybe not extremely reliable, but I shared the paper and may share the screen now just to show the picture for an excited state in tritium. So this is the spectrum that is observed in helium-6 alpha reaction on protons, so transferring 2 neutrons. And this thing is the ground state, and this is the excited state. Although the spectrum was really not that clean because the background had to be subtracted. So this was the starting point that the peak is visible. So here's the question. So if we confirm this experimental, and in fact, one of my postdocs, Cody Parker, is now working on exactly that using active target. If we confirm that there is this feature in the spectrum of alpha particles in the 2 neutron transfer helium 6 alpha to a proton. How can we be sure that this resonance, if it's real, that this resonance is actually a Efimov effect? Or is it something else? So is there a particular feature of Efimov effect that we can experimentally look for?
Is there an answer out there?
I think, I mean, I guess the first comment would be that if this is going to be the Efimov excited Efimov state partner of the Triton, then its quantum numbers should be 1/2 plus, right? So that's the obvious statement. And then I'd have to think a little bit more, and you probably know, Grisha, I talked to Jack about this too, right? The real signature and the thing that, for instance, in these beautiful Frankfurt experiments on Coulomb explosion of helium-4 trimers, they're able to do is that they're actually able to image the mass distribution. And so they can really confirm that the excited state is a copy of the ground state, related by discrete scale invariance. And so, and up to range corrections, that should be true in nuclear physics too. That statement that the excited state is a copy of the ground state related by discrete scale invariance is true also away from unitarity. It's just that the scaling factor changes. As was already emphasized, it's dependent on the mass ratio, but it's also dependent on the positions of the two-body resonance states. So, but I don't know how you do that. What I will say is that this Rupak et al. Paper argues that already knowing what we know about ND phase shifts in the 1/2 plus channel, there's evidence that there's an Efimov state hiding in the continuum, so to speak. Right. So in that sense, you don't need to go and find a 1/2 plus resonance, which I'm not even quite sure what that would be, since it's S waves with no Coulomb. You don't need to go and find a 1/2 plus resonance. It's about the signatures of that hole moving from the bound state region into the continuum region.
Okay.
Daniel, may I add just something to this? I mean, if you talk about the excited state of the Triton, this is not a resonance. This becomes a virtual state.
Right.
That's
Because
known.
because it's not a, because it's S waves with no Coulomb, right? So this has no barrier to get trapped behind.
And it goes through the atom dimer threshold, if you wish.
Yeah.
Well, clearly there's a lot of discussion room on this topic, and it wasn't my intention to spend all of our time on it, but there may be just a quick few things. In Dean's talk, he had this plot of alpha cluster correlations that's in a naive picture of solid alphas. You would climb up 1, 2, 3, 4, and so forth, and then you were over abundant because of nucleons could be in one alpha cluster or another. Isn't, and you use the word entanglement, and I can see that in a classical sense that word is appropriate. I'm not sure quantally, but doesn't that also mean that the alphas aren't alphas? That the clusters aren't really clusters? They're flickering or something.
Yeah, I would say that. I would say that the nucleons are not monogamous within one alpha cluster, but are shared amongst other clusters, and that makes Daniel blush, I think.
So in water, you probably know that H2Os form clusters, and they're not monogamous, and that leads to all the properties of water. Yeah. I had poked Yacide about his log FT, and it's just an issue that stopped me cold when I was reading their initial papers because it looked too low to be true. Can he make a comment about that? Because it would lend credibility to the exercise if it was a log FT that one expected.
So the log ft that was initially published were wrong. So we sent an erratum, and I think that the final log ft that we have, it's still low. It's of the order of 2.8.
So so let's just stop there. So if you have a log ft under 3, under super allowed,
yeah,
how are you supposed to believe what comes from it?
well, I mean, the whole thing is that everything is ruled by the error that we have within for the resonance energy itself. That's the thing. So I know that the limit
the log
the
ft
limit
is highly compressive. There's the log.
Yeah,
So,
I know that the limit for the super allowed is of the 3.4 or something like that. So that's
right.
the very low limit, of course. But our error is also very large. That if you see the final BGT, everything is possible in that regard, and that comes.
So can you give me a log ft value and probably asymmetric error bar?
Yeah, I have the asymmetric error bar for the BGT, which was 5.5, and the error bar was 8.3 and minus 3.3. So that's for the BGT. I don't remember if we have the.
And that was this correction with that was published?
Yes, that was what we published there. But again, what I want to point out again is that it's true that we may have a large error on the energy. Well, the status of this channel in particular right now is that I think that almost everybody agrees that this nucleus emits proton after beta decay. Now the question is where those protons are coming from. So that's the very first criticism that we also have. So with our most honest analysis, this is the numbers that we got with a large error bar, of course. And as I pointed out before, we obviously have a large error determining the structure of the resonance for low energy particles. And that's what we want to improve in the future. So that could be a very large error or source of error. And it's also true that one cannot rule out either that those protons may come from the isobaric analog resonance itself, as I mentioned before, but because one would have to explore a region of energy that is much larger, because the peak would be, it's very broad and it's at much larger energies, and explore how much of the tail goes inside that. But this is what the numbers that we have are those with a large error. That's the thing I can say, I can tell you right now regarding that.
Okay, other questions? We have a discussion period tomorrow. And I think we have an evening to refine questions for that period, so we can pepper each other with hard questions. Want to thank all the speakers. Any final parting questions here for today? Marek, did you want to say something? I guess not. So we'll see everyone tomorrow.